Hi, welcome to the video. In this video, I'm going to talk about the SDN network topology that I built for my cloud systems assignment for DCU at Dublin University as part of the blockchain master's course. So I'm going to cover a couple of different things in this video. First of all, we're going to talk through the motivation for the project, the technology that we used. We're going to do a quick demo of the application, and then a couple of just conclusion points just to kind of round off what we've talked about. So first of all, what's the motivation for building this? So as part of this assignment, we were challenged with coming up with a network system, data system that would require that we could prototype using some technology, networking development technology like SDN and Mininet. So the project that I chose was something that's quite familiar to me from my experience working in a blockchain infrastructure company. So blockchain networks have evolved over the years, and they've gone from simple software that runs on an individual's laptop to quite complicated deployments that can consist of many different nodes and lots of different services and technologies that all need to communicate with each other. And obviously, due to the high monetary value associated with some blockchain deployments, their networks need to be secure. And there's many reasons for this. There's keys associated with signing transactions and accounts and funds. There's also keys that are used by validator nodes, which are nodes that produce blocks on proof of stake networks. These keys are essentially like an identity. They're the keys that organization uses to generate blocks, which in turn generates profits and rewards from the block signing activities as defined in the protocol rules. So a typical validator node setup would consist of a physical server or even a cloud server, but essentially isolated away. And the best example here to use is a medieval castle where there's multiple layers to the castle. So you've got your moat and your outer walls, and these are your first line of defense. So in this scenario here, we've got the marauding Wild West people out in the internet trying to attack your validator. So the plan is that you set up these sentries, which are essentially your initial they're like the guard towers on your outer walls of your castle, and they're there to protect your validator from impending doom. Validator should never really be publicly accessible in any case, and the sentries are there as a kind of a proxy mechanism that can take requests from the public and distribute them back to the validator. So they're your first line of defense. And as you can see from this diagram, the best idea is to have multiple sentries in different regions and different clouds essentially as well. So this gives you the ability to have kind of failover in case a region goes down or a particular cloud is suffering a DDoS attack or certain different setups like that. And then as part of this, we will use VPC peering to connect between the VPCs securely, and then our Sentry nodes will interface with the public blockchain, and then the data will get sent to the validator over a private connection. And the validator should never be able to talk to the internet directly, so it should always go through the sentries. And if you think of the castle model, the sentry or the validator is your keep or your modern baby. It's the last line of defense, and it should never be compromised. So that's the kind of idea that I wanted to replicate using for this project, and to try and show where SDN and SDN technologies could be used to perform certain capabilities that we'll discuss later. So why prototype it? As discussed, blockchain validators are big business. If a validator is compromised, there's a potential for the rogue actor to do something bad, like double sign blocks or steal funds or kind of other activities which wouldn't be ideal for the company operating the validator. As discussed, the Sentry nodes give us that layer of security, but in the cloud, it's quite expensive to model these things. So one of the reasons we chose this project is because we can define these complicated networks using the technologies that we've chosen, SDN and the Mininet language, And we can do this relatively inexpensively. We could run the whole setup on a laptop, and there would not be any issues. So we can configure all the complicated routing and network protocols and all of the different controllers that are used in the network, and we can define that control plane on a laptop, and that would emulate a real life setup using multiple clouds and regions and VPCs and all of the lovely stuff that you get with the cloud. So what was the tech that we used? So as discussed, we're using SDN, which is a software-defined networks. It's a tool kind of framework that allows you to define various different networking components, and we can use those network components to add an overlay network to the physical infrastructure. So it's kind of like virtualization for network infrastructure, and it allows us to control the flow of data through the network, and also how the packets move and all the different routing. There's a good article here on Wikipedia that discussed the ins and outs and some of the more complicated features, and also the support that the SDN has in the industry. So there's quite a lot of different concepts, but essentially you have your applications, your controllers, your data path, and then the controlled data flow plane. So these are various different concepts that allow you as a developer to write code that works on certain parts of the infrastructure, and you can control the different layers and how data moves throughout the system. So that's a very quick high-level overview. If you want, you can check out the link here on Wikipedia, and you can get a more detailed information. So what else do we use? Mininet. So Mininet is a framework that allows you to model SDN networks and functionality. So it allows you to, it has a load of great features. It has a feature which we will show you in a while, where you can actually use a GUI to develop your network and to prototype the different connections, and then you can export the visual representation to code and also to a configuration file for later use. Very powerful and very flexible, and is a great way to rapidly prototype these SDN networks using Mininet. So what else do we use? So in order to use Mininet, it's predominantly works on a Linux environment. So in this case, I use VirtualBox and Ubuntu to install and configure the Mininet setup. So you can use a pre-baked Mininet image, but you may run into issues. You may not. Have fun if you want to try it, but you also have fun installing it yourself. So it's much easier to see how it all works when you install it yourself, and you can figure out all of the lovely complex issues to do with Python and various different pieces that will keep you up all night, full of entertainment. So they're the technologies that we used as prescribed by the assignment. So now we're going to go through a little demo just to show the network topology as described, kind of our Sentry node setup, and all the various different pieces. So remember that this is a locally defined network on a laptop. So the labels will describe what the certain features are, but you kind of have to conceptually grasp that this is a multi-cloud deployment with various different layers of infrastructure and various different setups. But I will try to explain it as we go. So here's a quick example of what the network looks like. I'm going to go through each of the layers, and then we'll actually go through the demo. We'll send some network traffic around the place. So in a blockchain network, it's predominantly a public network. There's multiple nodes can participate. They can come and go at any time, and they operate on the packet switching network, which is the internet. So these three nodes at the top are a subset of all the blockchain nodes on our network, on our hypothetical network. And these nodes are working away on the internet. They're talking to each other, they're communicating, and basically they are routing through S12 here, which is essentially the internet. So as we move to the next layer here, we've got US East 1, we've got S2, we've got EU West 1, and we got Northeast West, Northeast 1. And then we've also got this peer VPC 1. So we'll come to this guy in a minute, but essentially these three switches here are considered to be our regions in the cloud. So technically these are different regions. They could be in the same cloud, they could be multi-cloud preferably multi-cloud, to get a very robust Sentry node setup. Ideally, this will allow you to get kind of redundancy in case one cloud or one region suffers some sort of outage. In theory, you know, the more connections you have and the more Sentry nodes you have, the more robust your network should be. But there's obviously considerations with regards to pricing and complexity. The more complexity, eventually the less secure you'll be. So in each of these regions, we've got a single host, which we're calling Sentry 123. These hosts are a full blockchain node that basically interface with all of these public nodes. And as we talked about earlier, these sentries are the ones that really do a lot of the heavy lifting with regards to communicating with the rest of the blockchain in the peer-to-peer network. So these Sentry nodes are peered together using our VPC, and they are sharing information amongst each other, but they are also communicating to the wider public internet. So what's peer VPC1? So this is an interesting concept where a blockchain node operator may have a relationship with some other blockchain providers who also run infrastructure in the clouds. So in this model, instead of routing requests out through the internet and back in through the internet to reach this VPC, or to reach this peer in a tangential VPC, we can set up VPC sharing between the two operators. Essentially what this means is we will use the internal cloud network to route traffic between our two nodes, which both in turn are talking to the internet. So this allows us to actually reduce latency and to share information amongst ourselves rather than hairpinning in and out of the cloud. So this gives us a slight advantage, and it also gives us this trusted relationship where we know that data that we receive from this other third party is potentially trusted because we've set up this relationship with them. It wouldn't be in their interest to violate that data. But that being said, blockchains are untrusted world, so you got to be cautious. But thankfully, due to the cryptography involved, the blockchain nodes should detect any of these things. So in this example, we're using SDN. We suggest that SDN controllers be used at each of these locations. So we could use an SDN controller to control the communication between the peering and prevent the peer from accessing any other kind of network resources within the rest of our cloud. We also suggest that that a SDN controller is used as our kind of exit point for the cloud. So consider these nodes here, the cloud layer, and consider this the exit point to the egress to our data center. So for Cosmos, for instance, one of the best use cases for, we use a technology called a HSM to do the key sign, to store the keys that are used in the key signing. And a HSM provides a web interface, an API that's served over HTTP that you can use to request the keys that you need when you need to do a block signing. So we suggest that these are kept in the data center as the cloud doesn't support the keys that we need for the protocol. So essentially, we would use an SDN controller to configure how we route to our nodes, and then we would also use an SDN controller in the case of failover. So this EU West 2 is our failover region, and this may be in another cloud again, or it could be in the same cloud. But essentially, the thought process is that if our link down to our data center dies, we could use an SDN controller to automatically switch over to our validator in our backup data center. So I'm going to quickly go into the demo now, and you'll see the VirtualBox setup, and we can send some pings around the base. Okay, so here is our network, kind of like we described before. As you can see, we've got our nodes, our cloud, our backup center, and this shows the HSM setup that we talked about earlier. So the HSM is essentially, the validator is shielded completely from the public internet, which is up here, and we use our connections and our SDN controllers to route to our VPC, to our data center. And we have two links from our data center to add additional failover. And in this, we can detect where we need to route to based on criteria and logic that is happening on the blockchain, or whether our connections are dying, or if there's latency on a particular link. And the idea is that we can use the SDN controllers to control this network and to figure out when things need to happen. And likewise, to detect if we need to go to our failover environment. So I'm going to just do a couple of quick tests. In this example, I'm showing that the public Sentry nodes can kind of communicate with each other. And you can see that the public node is able to send information throughout the network to other nodes, to the other blockchain nodes. I'm now going to send a ping from node 1 to Sentry 1. Oops. So this is emulating the example where a node is trying to communicate with a Sentry node. And as you can see, it's found a route to the Sentry node. A couple of other routes, but our SDN controllers aren't 100% implemented to capture the additional traffic. So we also need to see, can our validator actually talk to the sentries? So in this example, this would be a validator actually communicating out to one of the sentries to receive information. So this is the kind of path that we would expect it to take, where it says, I need blocks, I need to sign transactions, I've got blocks, I've got transactions. So it should route directly to it and receive the data that it requires. And our controllers prevent it from actually going out to the public internet once it finds the best route. Again, similar if we wanted to send information from one of the Sentry nodes to the validator, it's also the same process. So at the moment, the controllers are trying to find out what the best route is. And if we were to have an actual controller implemented here, we would prevent any of these requests from happening, and we would route directly to the node that we want. So eventually we should find it. So another example is what we talked about with the HSMs. So we want to set up here where the HSMs can communicate directly with the validator, and they should go nowhere else. So in this example, we're going to ping the validator from the HSM. And we can say that, yes, this is the kind of connection that we want. So the validators can talk to each other through the HSM. The other interesting thing is here is the failover scenario. So we suggest that you should use, and this is kind of probably a controversial topic, but it's a suggestion that we would like to further investigate using this SDN network. We would like to build a controller that talks to the HSMs. And in the event that a link were to go down between our validator, or even our validator were to go offline. So imagine this link is offline. So in this case, our validator isn't able to talk to our Sentry nodes. So what should happen in this scenario? Well, if you're not signing blocks, you're not making money. So one of the things that we suggest is that we use our SDN controller to detect that the connection is broken and that the node is offline, and we remove this node from the active set. And we, at this point, route requests for our HSM, or for our validator to our HSM. So this node automatically comes online and takes over the block signing abilities. At the moment, this is probably a manual process for a lot of operators, or it could be semi-automated, but it's prone to risk, and there's a chance of being slashed by the protocol. So this is not an ideal scenario. We also suggest that in an example, say the link to our data center went down, or either both links to our data center. In this scenario where the links are down, we want to basically send requests using our SDN controller from Sentry node, let's go with 1, to validator 3. So in this scenario, we detect, oh, wait, our cloud links are down, so we should automatically fail over to our disaster recovery setup. And then when this comes back online, we could use SDN controllers to basically flip back. So there's a lot of things that we were trying to prototype here. We didn't get every single thing implemented because obviously there's a bunch of different controllers. And if you read the final report, there's actually a lot more discussions about how these different SDN features could be implemented and potentially could add huge operational benefits if implemented correctly to a cloud or a node operator as a service business, and also reduce some of the manual or semi-automated features and add extra extra security and information, and routing around how certain things fail over and how they do it and when they do it. So that's a quick overview of the demo. I'm going to quickly go back to the slides. So what do we find interesting? So the controllers and the SDN mininet use Python, which is a very easy language to use, and it's very easy to define protocol software switches, which is a great, easy way for a developer to build complex networks without having to understand how they work at a hardware level. So here's a very easy way to prototype networks. You can build complex things quite easy. As you've seen from our example there, we had a lot of different nodes, we had a lot of different routes, we had a lot of different features. And at each of those points, we could build controller logic that basically sits there and does dynamic routing or controls the data flow, which is potentially a very cheap way to prototype networks without having to use the actual cloud resources, which can be quite expensive. It's a potentially disruptive technology. So thanks for listening. It's been a pleasure.